array signal processing optimization in GNU Radio for tracking and receiving applications between ESL and French XLIM. So, Clément.
Good morning, everyone. Thank you for hearing today. Thanks for this introduction as well. So my name is Clément Campo. I'm a PhD student working for the French-German Research Institute of Saint-Louis, or ISL, and the XLIM laboratory at the University of Poitiers. And today I'd like to present you some feedback on the work some of my colleagues who are present here today and I carried out. And that consists in modifications we brought to our GNU Radio projectile tracking application. So I'll try to focus on practical aspects more than academic ones. During this presentation, I'll start by telling you a bit more about the context that motivated this work and how we ran into the need to change what we had already done in GNU Radio. And then I'll detail some of them. I'll start with our questioning of the hardware setup we've been using so far, such as the maximum data throughput we could exchange between our USRPs and our master laptop, or the recording speed we had at our disposal to for our measurements. Then I'll tell you some details we changed in our software implementation, before I conclude by explaining you a bit about a very specific need that we had due to our application. So first, as I mentioned, I'm part of the ISL, where we, with our team, we work, among other things, on projectile instrumentation and the implementation of secured communications between ground station and these projectile that we instrument. To do so, we've been using antenna arrays for a very long time. Indeed, they offer many advantages, among which the directive radiation patterns that can be dynamically reconfigured. So for those of you who are not familiar, here's a small animation of an antenna array made of a few antenna elements that's working in transmission mode. So of course, reception mode is the same reasoning. We'll be seeing that later. And in this case, you can see that all radiating elements are radiating the same signal, and the global wavefront is propagating perpendicular to the antenna array axis. But if you introduce some phase shift between your antenna element signals, then you can tilt that wavefront by a certain angle that you can control depending on that phase shift. And that's a very important property, as we will see later. That's what we're going to use. So for our specific application, we've been using a 4-element linear array that was designed at the ISL for 2.3 gigahertz applications. And in this application, we're willing to steer that antenna array using our USRPs and some GNU Radio blocks that we design here. And our goal is to perform projectile tracking, that is to detect the direction of the signal that is transmitted by a flying projectile and to favor reception in that particular direction at all times. So if you take the antenna array that I showed you just before and if you put it right at the median to the projectile trajectory, then our goal is to always favor radiation towards the flying projectile. Here's shown to you a quick schematic of our experimental setup. You can see that our USRPs are connected to the array and are controlled by our master laptop. And all stuff is gathered into a bunker for security procedures. So we had to use a remote trigger with a barycoaxial line. We'll see that later, how it influenced on our experimental setup. So here you can see a quick picture of that true setup. And our system proved able to follow a projectile flying at Mach 1 and above and record data at the same time. So far, so good, you may think. However, that was true when we ran our program at a 1 megasample per second sampling rate. problem was when we tried to decode telemetry data with a transmitter functioning at 2 megabits per second. That was too slow. So obviously we had to raise our sampling rate, and when we tried to do that, we encountered overflows. That is periodic losses of data, as you can see here, for a few seconds. And to give you an idea, our projectile flight is approximately 1 second long, so if an overflow occurs at that specific moment, then we get no data. That's something we could not put up with, so obviously we had a need for the optimization of our program so that it would be able to run at our objective 8 megasamples per second. Well, that brings us to questioning what we had so far. So first thing was, are we sure that our hardware setup will be able to handle the increased data throughput? So here you can see what we had been using in the first place, a simple Ethernet switch, and there's only one Ethernet cable, 1 gigabit, that was linked to the laptop. So if you make quick math, you will quickly conclude that's not going to be enough when you increase that sampling rate. So we decided to move on to a Thunderbolt 3 interface. And here, with 40 gigabit per second maximum of data throughput for the Thunderbolt, the limiting factor will be the Ethernet cables going from the USRPs, but in our case, that's going to be enough. So that's the setup we used for the rest of our experiment. Second point was that we were willing to be sure we could record our samples fast enough. So our laptop was equipped with a Samsung SSD that can write at a 520 megabytes per second as a maximum announced by its constructor. And we decided to add some DDR4 RAM that could write approximately at 21 gigabytes per second instead. So by implementing the RAM disk, we could go 40 times faster approximately than the SSD. So that's what we've been using in the following. Now that we're sure that our setup is not going to be the bottleneck for our application, that brings us to questioning the blocks that we have been implementing so far and try to rethink them, not only this time in terms of ease of implementation, but also in terms of performance. So the first thing was the data format we recorded. The native GNU Radio complex that are available are twice 32-bit data samples. But if you look into the USRP X310 that we were using, their converters and over-the-wire samples, we realized that was twice 16 bits. So obviously the rest of it are just waste of space and time when you record them. And we had to rather convert them back to twice 16 bits before we record them on our RAM disk. So here's just to show you the difference between the use of GNU Radio native blocks we had in the first place and then blocks to convert them back we used for the following. Once that was done, we decided to affect one or several of our processor cores to our most resource-consuming algorithms to make sure, excuse me, to make sure there would always be a thread available at all times when we needed to process their work function. So here you can see that for two of our blocks, we've been affecting one dedicated processor core that was only used for this algorithm, while the remaining of our less consuming functions had to share the remaining pool of our processor cores. Next point is the use of vector-optimized library of kernels, also known as VOLK. So that's a library of kernels using the single instruction, multiple data capabilities of the processor. So that's very good when you want to process a large amount of data with the same processing function. That's really nice because that's exactly what we are trying to do. So we took the bet of using VOLK as often as possible after we compared this very block with these two processing ways. And in our case, it appeared that using VOLK saved us around 30% execution time. So if we look at how we did that, you can see that this simple implementation for our block with Volk, only consisting in calling 2 Volk functions. And if you compare that with how it was done with the native sample loops inside GNU Radio, we see that that's really not a big deal in terms of implementation, so we are willing to do that to save that much amount of time. Now we're focusing on improving how we communicated information between our different blocks. So if you think about that, of course, the first thing that pops to mind will be the GNU Radio native tags. So as a reminder, it is metadata information that is transmitted from one block to the others within the data stream. So one tag is associated to one or several samples inside the data stream, and it will be seen by the receiver block at the same time it will see the data stream itself. And it's a one-to-one isosynchronous communication means as it was detailed and described in the GNU Radio documentation. Second way, as a native, would be messages. So this time, the information is transmitted to other blocks separated from the data stream. It will not be handled inside the block function, but in the subscriber outside, in a message queue that is managed by the GNU Radio scheduler, and it's defined as a one-to-n asynchronous communication means. And finally, I will present you quickly what we did with shared variables. We decided to add this way of communicating to us GNU Radio software and the ISL. And if we had to present it quickly, we would define it as the end-to-end asynchronous communication means that has to be used the following. So first, the user requests a shared variable pointer as for its variable ID. So you can see here an example when we're requesting a variable named DOA. And then we give the developer access to setters and getters, as you can see with write and read operation examples, to manage this shared variable value when it's needed. And if we had to give pros and cons on this way, we would say, as I told you, to end-to-end communication means that once it's implemented in an out-of-tree module, you can use shared variables in other out-of-tree modules by simply adding a line to your CMake list text file. We would also say that receiver blocks can read the shared variable whenever they will need to inside of their work function execution, so that can be controlled by the developer instead of being handled in the scheduler as with the messages, for instance. And that each block can update that shared variable at all times during its own work execution, so that will be instantaneously seen when other blocks start their own work function. And finally, it's thread safe. The first drawbacks that we could think of now is that there's no synchronizing or priority mechanism yet. So for concurrent write operation, that means that the last block to write a new value basically wins. And that there's no explicit link shown in the flow graph for this communication means. So if you're not accustomed to using them, that could make your flow graph a bit less readable. But as you can use these shared variable IDs as a string parameter of your block, you could always see which blocks are using these shared variables to communicate. And finally, I'll quickly tell you a bit about what I said was a remote trigger. As you can see here, we were not physically present in front of our laptop during measurement, so that's another constraint from our application. And to perform that remote trigger, we use this simple orange box you can see here to send a low-level pulse of around 10 milliseconds large on our coaxial line and received on the USB port. During our security procedures, we had a 10-second countdown before the firing. we were starting the recording of our samples 3 seconds before the firing and up until after 3 seconds. For, if you remember, a flight that is approximately 1 second. And to use that remote trigger that has to start after the run of your program, if you think about GNU Radio native blocks, the first thing we could think of was using the burst tagger blocks and propagating that trigger with the data stream as it's shown here. But that's something that really bugged us because when you're willing to increase the sampling rate just as we did, then you're just using a increasing resource-consuming way of propagating that trigger. So that's something we would definitely want to remove from our application. So I showed you the native way. So if I just use the data format I was telling you about a bit earlier, you will see that's not really changing our problem. And we were willing to avoid that at 8 megasample per second data stream. So our first idea was, okay, we went through the trouble of implementing shared variables, so let's use them. And here you can see that we used the shared variable we named trigger to do so. And we separated our trigger as a software data stream that we controlled with a throttle block at 1 kilo sample so that we would be sure not to miss the low-level pulse when it came. And we were at first very happy about ourselves because that made our program work without overflows in static configuration in our laboratory. But what we had definitely not seen coming was that additional 6-second delay that introduced between the moment we pushed our button and the moment it actually started recording samples into our files. So obviously, that was not the good way of thinking, and we changed our minds. So far, we are still not absolutely sure about why it introduced that huge delay. So if some of you are more comfortable, we would be more than happy to discuss that later. And then we went back to using the native messages in the radio for that trigger. And that allowed us to record our twice 16-bit samples with only a 1 megasecond delay after our trigger. So that's the thing we used. To quickly conclude, here's a small figure of what we got after we performed our measurement. So that's a measurement of the estimated angle between our antenna array and the projectile during its flight. And that showed us that we were on the good way. So you can see here that for 6 different shots, we have something quite reproducible between them. And that's still close to what we expected in the first place with a simple theoretical model. So that's just to summarize. We brought several modifications to our application so that we would be able to run it at 8 megasample per second on each channel. And to do so, we first made sure that our hardware setup would be able to handle the increased data throughput. We changed the data format and implementing a RAM disk to optimize the recording of our samples. We also allocated dedicated processor cores to our most computationally heavy algorithms to make sure there would always be a thread safe when they needed to execute. We used Volk as much as we could to save time during processing and reduce the number of streams between our blocks, even though that could seem tempting at first because of its ease of implementation. Finally, we also used and implemented a thread-safe shared variable communication means that could fit some very specific needs for some applications. And finally, we adapted our remote trigger so that it would fit the particular needs related to security procedures when we're firing projectiles. And with all these changes, we finally managed to run our application at 8 megasamples per second without any overflows. So that's what we wanted to share with you today. I really thank you all for your kind attention. I will do my best to answer questions if there are. And if you have some things you could advise us with on some things we haven't implemented yet or that could be improved, we would be really happy to share about that later. Thank you all.
So we've plenty of time for a few questions. So do you have any questions about Clément's work? Is there another mic to pass to the audience, or is this the only one? Oh yeah, okay.
Questions?
People are really shy. It's the beginning in the morning. Oh, there's a question. Okay.
I have one question regarding the USRPs. Did you sync them somehow, like the oscillators, or not at all?
Yes. Yes, we used two USRPs that we synchronized using an octoclock with PPS and 10 megahertz reference, and that octoclock was fed using a GPS signal.
Okay, thanks.
Thank you.
Hi. I have a small question, which is, you said that you can't be near your computer while you are starting the measurement, and you use a coaxial line to bring the trigger, but why not use just the Ethernet line between the Etus and your computer and keep your computer in the bunker?
Indeed, that's something we would really like to do. Our problem with this is that the coaxial line was already buried inside, so that's something that's available. We are not the only ones doing our measurements at that time. You can imagine firing projectiles takes a lot of staff. We have people specialized in pyrotechnics, for instance, ballistics, and we are sharing equipment with them. And vehicles are also, people also drive vehicles in between, so if you don't bury your line, you're facing the risk to damage.
I'm not familiar with your work, but do you already steer the transmission towards the projectile?
I think for this specific application that we showed here, the transmitter was omnidirectional. We have been performing directive transmissions on projectiles in previous studies. I think for this one, that was not the case.
But then is there a closed loop eventually?
I'm sorry?
Will you be eventually using a closed loop, like using some Kalman filter type thing?
That would have to be discussed. So far, we are not doing it for these specific ones. I would not be able to tell you if they're planning to do it on a short-term or long-term plan.
Thank you.